Okay, so hi everyone, and thanks a lot to the organizers of this very nice workshop for having me here today. I will discuss isospin-asymmetric QCD matter and some applications of our lattice investigations. So for the lattice part of my talk, these will be results that I have obtained together with Bas and Brandt and Gergo and Rodi at the University of Bielefeld. So to jump right in, I just want to very quickly set the stage, even though that might not be needed for this audience, by discussing where we can find in nature hot, dense, and well, actually also magnetized, even though I will not talk about that aspect in my talk, states of strongly interacting matter, not just any states, but those that are at the edge between the hadronic phase in which quarks and gluons are confined within hadrons, and other phases such as the quark-gluon plasma, or phases characterized by, for instance, pion or kaon condensation. Now, one possibility for that is to take a huge step back in time and look at the first few microseconds of our universe's evolution, when the universe was basically a hot, strongly magnetized primordial cosmic soup. Another possibility is to go to the microscopic distance scales over which heavy ion collisions experiments are looking at the evolution of the fireball created by the collision of heavy nuclei. And this happens at very hot temperatures and about the nuclear saturation density. And actually the magnetic fields created in these situations are the strongest on Earth. We can also go back for a moment to the cosmos to observe that violent astronomical events, which are the binary neutron star mergers, are also a situation in which we have, perhaps slightly smaller temperatures as compared to heavy ion collisions, but densities up to twice nuclear saturation density and rather intense magnetic fields. So that's what we want to be looking at. And there is a fourth possibility, and that's simply looking at the interior of these compact astronomical objects, which are characterized by even smaller temperature, but that are the most neutron-rich and dense objects we can think of possibly. Okay, with that stage set, and if we set the magnetic field aside for a moment, I would roughly say that the situations, the physical situations that I mentioned can be sort of located somewhere in this very well known and many times displayed in this workshop sketch of the QCD phase diagram in the space of temperature, net baryon density, and somehow there is a third axis, even though the phase diagram is not represented here, which is the axis measuring the imbalance between the number or the density of neutrons and the density of protons. Now, at this point, I must say also what is the tool that I am employing for my studies, and that is lattice QCD. And with that as a systematically improvable ab initio non-perturbative technique that we can employ to learn about the phase diagram, we also have to say that there are limitations. And these limitations come from the fact that if we go to the, if we take into account that we're working into a grand canonical ensemble and we trade the density for the chemical potentials in some basis that can be set, like the one I have on top of this slide, then only the case in which we have a non-zero isospin density is suited for lattice simulations. In that case, the skew hermiticity of the Dirac operator is not spoiled by a non-zero isospin chemical potential. Basically, you assign the same quark chemical potential to the up and down, but with different signs, and you recover reality and positivity of the quantity that we would like to interpret as a probability density function in our path integral that we solve on the lattice. Instead, for baryon density, you have the infamous sign problem or complex action problem. And actually, this is, of course, what prevents us from saying something about very key and important features in this diagram, such as the critical endpoints. Okay, I want to focus today on a phase diagram that we can simulate, which is the one at finite temperature and non-zero isospin density. I will start by knowledge of that phase diagram that comes from basically chiral perturbation theory and perturbation theory applied respectively in the limiting cases of 0 and very, very high isospin densities. What we learned from the first limit is that at some point we cross the onset of a pion condensed phase. Even at t equals 0, there is enough energy to create charged pions. These are bosons, they condense, and a Bose-Einstein condensate phase is formed through a boundary which is of second order. If we then consider applying perturbation theory at very large densities or chemical potentials, this was all done by Sun and Stefanov in 2000, by the way, then an attractive gluon interaction leads to diquark pairing of the BCS type, and in particular, the expectation of the formation of a superfluid BCS phase of pseudoscalar Cooper pairs was formulated already back in 2000. Now, another observation was made, namely that since the symmetry breaking patterns and the quark number of the condensates are the same in the Bose-Einstein condensate phase and in the BEC phase, this and that, then it is plausible that the two phases are not separated by a phase transition, but rather connected by an analytic crossover. Now, as I said, one can study non-zero isospin on the lattice. Very importantly, one has to be aware about the symmetry breaking patterns, because then more terms will be encoded in the fermion matrix, namely at mu I different from 0, you enlarge the fermion matrix at mu I equal to 0 with this term, and this then corresponds to the spontaneous breaking with some pion condensate of this form and of this symmetry, of the flavor symmetry, and in particular to the appearance of a Goldstone mode. In principle, we could stop here. However, this would not be something we can simulate on the lattice. We would have a 0 mode. Then we have to add one more term to the fermion matrix in order to explicitly break that symmetry. This is what we call a pionic source, and that is a necessary infrared regulator, and it triggers spontaneous symmetry breaking in a finite volume. However, we want to extrapolate it back to 0 at the end because it's not something physical. So with that in mind, the existing investigations from a lattice perspective of the phase diagram have already done a lot in unveiling phases in this temperature versus isospin chemical potential phase diagram, namely by looking at the renormalized chiral condensate. The chiral crossover region was drawn on this diagram, and the Bose-Einstein condensate phase boundary, a second order boundary, can also be drawn by looking at the corresponding order parameter, which is the pion condensate. Of course, it's renormalized version. And yeah, that would be it, but I told you that perturbation theory also predicts the existence of a BCS phase. So there are more phases to unveil in this phase diagram, and that's why I will now discuss this as a first application and the first part of what's left of my talk. Then I will sort of accompany you in a journey beyond the phase diagram, in particular towards the equation of state. And we will see how we can use the equation of state as calculated from the lattice in order to feed it to a model that predicts what are the conditions that could accommodate pion condensation in the early universe. So let's start from plain phase diagram, and let's see if we can, from a lattice perspective, find confirmation for that BCS phase, which so far has only been predicted on perturbation theory grounds. One conjecture has been made, and that's one of the two, I would say, guiding principles for this investigation, namely that when one looks at the Polyakov loop as an observable, which should be sensitive to going from the hadronic phase to the quark-gluon plasma phase as a result of incrementing the temperature, one observes that one can draw isoline of the renormalized Polyakov loop, and that high, or rather high value, which are as high as what they are at the crossover transition at μ=0 can be observed for the Polyakov loop even inside the pion condensed phase. So what's that supposed to mean? And it also, as you can see, it's not sensible really, it's not sensitive really to crossing this phase boundary, the signal from the Polyakov loop. What's that supposed to mean? That perhaps the crossover between the Bose-Einstein condensate and the superconductive BCS phase might just be connected to the deconfinement crossover. Now, this is a conjecture. What we would then have on the two sides is either tightly bound pions in the BEC phase or weakly bound Cooper pairs. And in particular, in this BCS phase, we would have a sort of a super fluid or superconducting, if you take into account that these are charged particles, ground state with deconfined quark. That's what we are after. And we started looking for this, or looking for signatures of this phase in the Dirac spectrum. So let me then tell you a couple of basic properties of the Dirac spectrum in this setup, namely that it has complex eigenvalues. You can show that it satisfies this relation, and therefore left and right eigenvectors do not coincide. You can also show by employing symmetry-based relations, chiral symmetry and gamma phi hermiticity in the staggered sense, that for every eigenvalue in the up sector, there is a complex conjugate eigenvalue in the down sector, which is what makes the determinant real and positive and our simulations doable in the first place. Moreover, we have the technology to measure a spectrum, even though it's complex. We can, for instance, look at the lowest 100 something eigenvalues. We can analyze the spectrum. We can look at the spectral density in the complex plane by using analysis techniques such as kernel density estimation as a non-parametric way to estimate the multivariate probability density function from the measured spectrum. However, I should first tell you why we look at the Dirac spectrum. And this is what I'm trying to say with this slide. We know from the Banks-Kasher relation at μ=0 that spontaneous chiral symmetry breaking is reflected into the infrared limit of the Dirac eigenvalue spectrum precisely through that relation. And you observe an accumulation of near zero eigenvalues. At μ be different from 0, the non-positive definiteness of the fermionic measure has the effect of rendering, first of all, this density rather undefined, and the connection between the condensate and the density of eigenvalues of the complex Dirac spectrum is very much more complicated. However, as we are only at μi different from 0, while the baryon chemical potential is 0, we have the advantage that the fermionic measure is still positive definite. And in 2013, a very useful for our purposes relation was obtained, namely one that connects the density of eigenvalues of the complex Dirac spectrum directly through a proportionality factor to the BCS gap, precisely what we would like to see as a smoking gun for a BCS phase. So that's the plan. And I can show you some results of our measurements based on the Dirac spectrum, which are summarized in this animation, where you can see the spectrum itself in the complex plane. And now time is given by the isospin chemical potential, which is growing. And you see that something happens to the spectrum, and we want to interpolate it to our point of interest, which is 0 in the formula, but in our case is the mass of the bare light quarks, because we are doing simulation at non-zero masses. So what happens is something that I can easily sort of condense into the phase diagram itself, where you can see the Bose-Einstein condensate boundary, and you can see some dots with a color code that gives you the spectral density, how large is rho of MUD. And there's something nice and something ugly about this. The nice thing is that the onset of a non-zero density corresponds to the onset of the Bose-Einstein condensate phase. You can see I only have blue points on this side of the boundary, and here suddenly I have some non-zero density. However, towards larger values of mu I and smaller temperatures, which is where I would expect to immediately then go through the crossover between the BEC and the BCS phase, I have a decreasing function when I look at the density. This is explained qualitatively by the fact that at small chemical potential, you have almost a vertical line in terms of the spectrum, which is to be expected, knowing what happens at mu equals 0. Then this encompasses the red dot, but at some point it just changes in a way that the density at our point of interest goes back to 0. But does it go back to 0? Actually, when we perform our simulations and we observe this drop, if we look at more temperatures, we see that as soon as we are above almost everywhere in the quark-gluon plasma phase, this is really something which is 0 within errors. However, for small temperatures and large isospin chemical potential, we have something that I can tell you is different from 0 outside the error bars. So what do we conclude? That we can certainly read out of the density signal the points at which we access the Bose-Einstein condensate phase from the hadronic phase. However, it is not entirely clear in what sense the signal reflects the crossover boundary, and we keep looking at it. So that you access the BEC is made even clearer if you correlate your measurements of the density with the measurements of the Polyakov renormalized, and then you can see that there is an onset precisely where the renormalized Polyakov takes the value that it takes crossing the boundary. And one more positive note is that this small value outside within error bars that we get at large mu I is not too far from what you would expect from perturbation theory calculations. So yeah, I think I can skip this. This is more or less what we have as ongoing research on the BCS phase, and we will carry on more simulations to clarify the meaning of these results. But before my time is over, I want to, as I said, bring you on a journey beyond the phase diagram at non-zero isospin chemical potential, namely looking at the equation of state. So we want to look at the equation of state, which describes our matter at equilibrium, namely the relation between the pressure density, how the pressure density depends on the temperature and the isospin chemical potential, and what is the interaction measure of or trace anomaly, however you want to call it. And this is another investigation that we are sort of carrying out. Our key observable in this case is the isospin density that we obtain from lattice simulations, and we then spline, interpolate with a two-dimensional spline that we can then feed into this integral that's supposed to give us back the difference between the pressure at 0 and non-zero mu I at fixed temperature. These results, P of t and 0 and I of t and 0, we can use, they exist in the literature, and we are able to obtain the pressure difference and the trace anomaly difference. What you see if I plot for you the isospin density as a function of the chemical potential is some growing behavior whose onset happens at small temperatures right at the phase boundary. And one can also redraw the phase diagram in the plane of temperature and isospin density, and nicely connect to chiral perturbation theory results at small temperatures, and even attempt a first continuum limit. When it comes to then using the isospin density and go to the other thermodynamic variables we are interested in, so the energy density, the entropy density, the pressure, and the trace anomaly, here are the results that we get for different temperatures, and in this case at one fixed value of the temporal extent of the lattice, that is at one lattice spacing. I don't have time to go into the details. I guess the effect I want to point out here is that at low T, one really sees the onset of the Bose-Einstein condensate phase in this signal. Namely, there is a non-monotonous behavior of both delta S and delta I with mu I at low temperatures. That is evidence for pion condensation. And this is very well visible in the interaction measure because of the different rate of rises of the pressure and energy density. Now, these are lattice results. They are interesting on their own, but sometimes you want to complement them with some model calculations if you want to make non-trivial predictions, such as what are the conditions that might have accommodated pion condensation in the early universe. And this is the last application I want to talk to you about today. What we did is we employed, together with our phenomenologist colleagues, our results on the equation of state at a very low temperature in order to calibrate a variant of the hadron resonance gas model that incorporates pion condensation. It does so by replacing in the pressure the free pion gas with an interacting pion gas modeled by a quasi-particle approach, while the other hadrons are free. And then we can test this model by comparing back with equation of state results from the lattice at finite temperature, such as the one that I showed you in the slide before this one. Why do we need that? Because what we are doing is assuming isentropic evolution, and we are computing the cosmic trajectory of the early universe in a 6-dimensional space of the temperature and all relevant chemical potentials by solving these evolution equations, these 5 evolution equations you see on the slide. And on the left-hand side of the equations, you always have a density over entropy density. And this is what you can use the lattice results combined with the model for. And on the right-hand side, you basically have some constraints. For the right-hand side, you basically have some constraints. And the motivation for this work, from which we got at the end that, yes, indeed, under some circumstances, the trajectory of the early universe goes through the pion condensed phase, comes from the fact that already in the past, in these 2 publications, it was observed that unequally distributed lepton asymmetries are sufficient conditions for pion condensation. And it is meaningful to think of unequally distributed lepton asymmetries. These are conserved separately, family by family, due to the fact that there aren't neutrino oscillations at these temperatures. And what we have on top of that is, on top of this constraint, which we sort of naively fulfill because we set the total L to be simply 0 via this relation, is we can also use the known, very precisely known value for B. So if we do that and we combine lattice, the model, and the astronomical constraints, we can obtain as a result the fact that indeed pion condensation might have occurred for unequally distributed lepton asymmetries that satisfy this relation over here, which you can see is like where vertically on the left and on the right, you access the gray areas in this temperature versus lepton asymmetries phase diagram. This has important observable implications. In particular, there is imprints of condensations, both in an enhanced relic density of primordial gravitational waves, which might be detectable by future observational campaigns. And it also has an impact on the mass distribution of primordial black holes, equally as important. Not clear if and to what extent that is really observable very soon. However, yeah, those are the 2 applications, and our phenomenologist colleagues have helped us coming up with them.
So you have 5 minutes.
No problem, because I am, as you can see, already displaying the summary slide over here. So I basically discussed 3 main topics and correspondingly 3 main results with you today. First, I discussed about more phases to be unveiled in the temperature versus isospin chemical potential phase diagram, namely the superconducting BCS phase. I told you we are currently looking at Dirac spectrum, and that is teaching us something about the phase diagram. Let's see if there is a smoking gun for the BCS to be find out of that signal. Then I showed you some results about the equation of state. Most of the results I showed you were actually at finite value of the lattice spacing, but on the summary slide, I have this plot to show you that actually more simulations have been run at different lattice spacing, and the continuum extrapolation is being carried out currently. These are 2 temperatures and 3 different values of n tau for these 2 temperatures for the interaction measure or trace anomaly. And last, though it might have been quick, we can come back to that in the question session. I discussed with you the pion condensation in the early universe that, yeah, it's plausible for if a relation on lepton flavor asymmetries is satisfied, which has this form, in which case the cosmic trajectory, rather than being the one very close to the t-axis, goes through the pion condensed phase with interesting phenomenology, observational consequences. So that's all I wanted to say today. I thank you for your attention, and I'm eager to welcome your questions.
Thank you very much. So we had time for questions. Okay.
Well, thank you, Francesca. It's a very nice overview. And so, as you say, this pion condensed phase is really worth more discussions, and very naive question that comes to mind. But is this really relevant to have only finite density of isospin, or we should really consider also non-zero baryon density? Because technically this, of course, makes a difference.
Yeah, it technically can make a difference. So at the moment, we basically used first of all, lattice results that are produced at non-zero isospin chemical potential. And you might have noticed that the label of this axis is actually charged chemical potential, because in the model there is charged chemical potential and a very low baryon chemical potential. So what you get is, like, by solving the evolution equation, you get out values of these chemical potentials. They are sort of the output of that calculation. And now, mu b is actually small, and the fact that here we have mu q instead of mu I is not that much of a concern. First, because at t equals 0, the two are the same as soon as you don't have kaon condensation, which you don't have for, which is sort of, yeah, improbable if there is pion condensation, and for low enough values of mu. And at non-zero temperature, we did the experiment with our lattice results to look at deviations in the phase boundary, and we sort of found very slight effects from having a mu q instead of a mu I. So given that, so given the framework or the setup where we have lattice results and where the model is driving us, that's what we can conclude. But I agree with you that one should look into, yeah, other models, and at that point having a non-zero mu is certainly crucial, and we should rather think of maybe Taylor expanding our non-zero mu I results in that direction, to say the least.
More questions? Okay. I have just a naive question. So why the pion condensation would affect gravity waves?
Ah, very good question. So let me bring you to the plot that sort of shows precisely the effect. So we are talking primordial gravitational waves. These are due to variations of the Hubble expansion rate that can, for instance, come from phase transitions. So for instance, from having gone through a pion condensed phase. So that's qualitatively the expectation. You have a phase transition and therefore this varies the Hubble expansion rate and therefore there are observable consequences. And if you want the quantitative consequence, this is what you have in this plot, which I am definitely not the expert that should explain that to anybody. However, you sort of can see that when we go to non-zero and unequally distributed lepton asymmetries, in some case we have some effects that these lines are shifted up, for instance, as a function of the non-zero lepton asymmetry. And this might be something that SKA20 will be able to measure.
So it's essentially due to a modification of Hubble expansion?
Yeah, qualitatively, that's the...
Okay. So if there is no other questions, we thank Francesca. We move to the last talk.